Okay, good morning to WinDoor Day 2 and our educational sessions. First, I'd like to recognize our sponsors, Screenco Manufacturing, Elton Manufacturing, the Sagania Group, and UL Solutions that sponsors our Learning Lounge. And I'd like to welcome Carrie Sheets with Quanex. Quanex is our WinDoor presenting sponsor, and she's graciously offered to introduce our first session for the day.
Good morning, everyone. Like I said, I'm Carrie Sheets, Marketing Manager with Quanex. I'd like to invite you all to visit us at booth 1004 to learn how we are not just another manufacturer, we are a part of something bigger. And I would also like to go ahead and introduce our next speaker for this technical education session, Glazing for Comfort, presented by Al Ugalis with Fenestration Canada. Thank you.
Thank you. Thank you for attending our session. Can you folks hear me all right here? Okay, great. So our topic today is glazing options for thermal comfort. And I recall, discussions on this subject going back 10, 12 or more years at Fenestration Canada, the Canadian Window and Door Manufacturers Association before that. And we've talked about solar heat gain coefficient. We've talked about this, we've talked about that. But I had been frustrated that somehow we hadn't had a good handle on really appreciating. That's great. I may want to avoid high solar gain when I've got large windows. I may want to avoid cold surface, cold glass when they're large windows. There are times when the passive solar gain may be beneficial or helpful. But when it comes to choosing or specifying a product, exactly, there are like 1,000 glass options. Where do we begin the discussion around glass and thermal comfort? So earlier this year, out of that frustration, I started going back to some simulations I had done years ago when I was working for a window manufacturer. And I was looking at this table of simulations and saying, what can I learn from this table? And I started playing with it. And I'll stop right there, but because I'll describe what I did later as I show you the summary findings of what I did as I basically zoomed out to, 1,000 feet and then 5,000 feet to look at the data. And sort of the farther out you zoom in terms of the level of precision of something like a U factor, the clearer the patterns begin to come. And so, so that's what I'd like to share with you. But first, we'll start with just some basic important thermal comfort concepts. And this is not. Okay, good. So this presentation aims to present a new approach to selling occupant comfort in buildings of residential occupancy. The thermal and comfort properties discussed apply to the vision area of the glass and do not include the effects of window and door frames. Separating glass values from overall product values allows us to focus on the glass, the window component that has the greatest impact on thermal comfort. And it's interesting that, most of the goodness in our windows and doors comes from the glass. You can have any frame system and performance will change dramatically depending on the glass that you put into it. So when it comes to solar heat gain coefficient, you can actually ignore the frame because it's all coming through the glass except for a couple %. And similar for U factor. So really the choice of glass is the key decision that you have to make. It's more important than the choice of the product or the framing system. So thermal radiation and comfort. It helps to understand some basic concepts about heat and how we as humans relate to hot and cold surfaces and whether they're close to us or farther away. So we talk about radiation, and something that we probably don't think of every day is that all objects emit invisible thermal radiation, with warmer objects emitting more than colder ones. Basically, if you're alive, you're emitting thermal radiation. In fact, everything in this show hall, including the concrete floors and the steel, is emitting thermal radiation. Everything above the temperature of absolute zero emits thermal radiation. So the moon, emits thermal radiation, even though it's in the frozen wastes of space. So, but how we sense it, how it affects our perceptions is that think of putting your hand in front of an oven door. We all know what that feels like, right? You will feel the radiant energy emitted by that warm surface. Your hand also radiates heat to the oven too. It's just that there's so much more heat coming from the oven than is in your hand. That's why you're feeling the oven as a warm object near to you. Similarly, imagine that you're touching a single glazed window in winter. I'm sure we've all had that experience. So those of us with gray hair at least have been in homes, grown up in homes with single pane windows. The cold glass and your warm hand are both emitting thermal energy. There's still energy in that glass and there's energy in your hand. But since your hand is warmer, it is emitting more towards the window than it's gaining, and you feel a cooling effect. Thus, a cold glazing surface in a room chills everything else around it. And this is how we experience warm comfort, but also cold discomfort or overheating discomfort. And by the way, this text comes from the therm simulation manual. So they want to make sure the people who use it understand the basic concepts, which helps all of us. So as I said, all matter with temperature greater than absolute zero emits energy. The interesting point on this slide that I want to focus on is that shiny metal surfaces, which have low emissivities in both the visible wavelength and in the far infrared, can be used to reduce heat transfer in both directions. And basically, that's what a low E coating is. A low emissivity coating is shiny metal particles, primarily silver, seems to be the one we're mainly using in low E coatings these days. And it's these silver atoms, applied to the surface of glass at a certain density that actually reflects different wavelengths of radiant energy. So high frequency energy like visible light goes right through it. Lower frequency, let's say the low infrared energy in a warm room is reflecting off that glass. And depending on the nature of the low E coating, it might be emitting more or less of the solar heat from the sun because of the density of the metal particles on the glass. So that's the technology behind our low E coatings. And effectively, it's acting like a heat mirror. You all remember there was a product called heat mirror. Essentially, that's what low E coatings are. So when we talk about emissivity, emissivity is the part that doesn't get reflected back and makes it through that dense package of shiny particles. So when we talk about conventional uncoated clear glass, it has an emissivity of 0.84. That means that if whatever amount of heat you try to apply to that clear glass, 84% of it's going to go right through, only 16% gets reflected back in. If we talk about the early generation of pyrolytic low E coatings, we're looking at emissivity somewhere around 0.2, where 20% is transmitted and 80% is reflective. So these made a huge improvement to the thermal performance of windows. And of course, the best coatings we have now in terms of the lowest emissivities are in the range of 0.02, which means only 2% of that radiant energy is passing through it, 98% reflected back in. And that's the magic that makes the glass such a important component of window products. So these coatings are the single greatest innovation in the energy efficiency, solar heat gain control, and the comfort performance of window glass. We have argon fill or other dense gases. We have warm edge spacer systems, but they help, but just less than the glass does. And of course, we can combine these low E coatings with one or more glass layers to provide significant control over both shorter wavelength solar radiation as well as longer wavelength radiant heat from building interiors. And it's important then to understand that this emissivity, this heat transmission and heat reflection properties have a direct bearing on the comfort of building occupants. So there's several ways we perceive cold discomfort. One, and there's a whole science around comfort in buildings. And, you know, we have an ASHRAE standard 55, which deals with how you can model and try to estimate the conditions under which people will feel comfortable and uncomfortable. One of the things in that standard is that when there's a temperature difference that's greater than about 4.5 degrees Celsius between two surfaces, let's say one wall is colder, one wall is warmer. If there's less than this temperature difference between them, you'll probably feel comfortable in a space that has both. But when there's more than 4.5 degrees, when it gets to 5, 8, 10 degrees difference between surfaces, you really start to feel the cold discomfort. It's important to appreciate that because we're going to look at glass surface temperature as one of the metrics of comfort. So in this case, we have a situation where this is a home with a large double glazed window under NFRC winter conditions. The indoor temperature is 21 degrees. The exterior temperature is -18. And with a good vinyl window and a glass in it with, let's say, 2 low-E coatings, one being, no, this would be just a single low-E coating. Your indoor glass temperature is going to be about 12 degrees under these conditions. So there's going to be like a 9-degree difference between the room temperature, the wall temperature, and the window. And you're not going to feel that comfortable near the window. You'll want to be sitting away from it. If that window was double pane clear glass, you'd be farther away from it yet to feel that. But this is how we perceive comfort. And this is why things like glass surface temperatures are important. If you were now to take the same home and put into it a triple glazed window with 2 low-E coatings inside of it, surfaces 2 and 4, you'd be having a glass surface temperature under these winter conditions of 17 degrees Celsius, just 4 degrees or so different than your 21-degree radiant temperature. Here's a case where you're not going to feel significant cold discomfort near the windows. And this is the whole idea behind passive house buildings and why passive house windows are always triple glazed, is because they want you to be as warm beside the window as you will be far away from it, which means that then you don't have to have space heating at the window. You don't have to have a duct pumping warm air or a radiator or some other heat source to overcome the discomfort of the window. The window itself is providing you a sufficient level of comfort. Oh, and this is an engineer in Winnipeg boasting about his triple glazed modern low-E windows. It's -21 degrees outside, and he's boasting about the fact that his glass temperature is at around 22, and even the coldest part of his windows, the frame corners, are at 18 degrees Celsius. So these are conditions where, yes, of course, you're going to feel comfortable beside a window like that. And there are, you know, many companies in Canada offering these products just like that for sale today. Let's review the thermal performance metrics briefly. We know that NFRC U factor is the heat flow out from the building. It's measured, it's in a 1-hour rate. So it's the heat flow over 1 hour in watts per square meter per degree of temperature difference. So if you want to know how much heat goes through your window, take the temperature difference, multiply it by the U factor, and that'll be your watts per square meter. Solar heat gain coefficient, we've all heard about that a lot. It's the proportion of solar radiant heat transmitted through glass into the building interior. The trouble with solar heat gain coefficient, it's hard to know how that's going to affect your comfort, right? What does a 0.3 solar heat gain coefficient feel like compared to a 0.5 or 0.6 solar heat gain coefficient? It's just a ratio. There is a metric generated by the WinDoor program called relative heat gain. And the only reason I know about it is when I taught myself how to use the window program, 10, 15 years ago, I hadn't read all the manuals and I wasn't sure how to export data from it, but I saw that you could actually push a button that generated a report. And when it generated the report, it gave you all the data that the window program has worked with. And it contains some metrics like the glass temperature, the winter and summer glass temperature on the inside, as well as the outside of the glass. And it gives us a metric called relative heat gain in watts per square meter. And that is a kind of a worst case solar heat gain capturing scenario. I was asking an engineer, where did that metric come from? And he told me that they don't use it anymore, but the mechanical engineers used to use it to estimate their maximum cooling load for glass towers. So it's your worst case, west facing, setting sun, coming horizontally through the window glass. And glass manufacturers would rate their products with these relative heat gain numbers, and engineers would use those numbers to size their mechanical systems based on the relative heat gain. So it's a number that, it may not be used in whole building energy modeling today because they have more sophisticated metrics. But I think it's a useful metric because it tells us the worst case heat scenario that will come through a window. And it doesn't do it by a ratio like a percentage, it does it with watts per square meter. And if you multiply 500 watts per square meter times 3 meters of glass, you get 1,500 watts. That's as much heat as a typical space heater generates, right? Or other appliances that you may be familiar with. By the way, am I being too loud? Is this good? Okay, thank you. So the relative heat gain, new, old metric, computed automatically when you do a window run. When you design an IGU in window, not an IGU, but really just glass layers, it will generate the relative heat gain number. And this just says what I just told you, right? It's another way to think about the heat coming through a window or door if you can relate it to the number of watts coming through it and based on your own personal experience with things like space heaters. So now let's look at what I discovered by my trying to zoom out to 1,000 and 5,000 feet, looking at my data to see what I would learn from it. And honestly, I was surprised because I saw things I had never noticed before. And because my table had indoor and outdoor glass surface temperatures and relative heat gain columns in it, I was able to appreciate those numbers too. Whereas I think many people who use that program, window program, and they use Therm to do energy modeling, they may never look at those numbers. I don't know that they ordinarily appear in the interface. So let's look at our toolkit. We have a toolkit. We have only so many glass configurations possible these days that are cost effective. And so the most common things we have in our toolkit, besides the R1 and R2 glass that we're trying to replace, are dual pane with one low E coating on surface 2 or surface 3. If you're in the West Canada, you're going to have it on surface 2 to cut down solar heat gain. If you're out here on the East Coast or Central Canada, you've got it on surface 3 to maximize the solar energy from the sun. Both of those are at R4 level. And this is inch pound R4. So R20 insulation, this is the same R number we're talking about. Our next option is an R5 window. Add one more low E coating on surface 4. This is one step up from the R4. The next option, if we add one more pane of glass and another argon layer, we can now convert that R4 window into an R6 window. And we can put the coating on 2 or 5. If you're aiming for high solar heat gain, putting it on 5, of course, will actually give you the highest solar heat gain in this configuration. The next option is to put in 2 low E coatings. It'll have lower solar heat gain, but it'll have other properties that we're going to see as well. And that brings you up to R8. And that's basically the level of product that Passive House windows are using. You don't need any more than that to actually achieve passive house ratings. And the hard part of designing a passive house window isn't just the U factor. It's actually making sure that no part of the product has a temperature that could lead to mold growth at a very high relative humidity and a high temperature. So that hygiene criteria is what makes it tough to design a passive house window. If it was just U factor, well, we can do that with windows we have today. And then here it is, R9. If we actually have 3 panes, 3 low E coatings, we bump up 1 R value from R8 to R9, and we get a slightly more energy efficient piece of glass. So these are our configurations. We have 1, 2, 3, 4. We could say 5 options of upgrade over the base glass we've been using. So basically, I'm focusing here just on clear glass. You know, with tinted glass, all the numbers would be different. But we're looking at the 5,000-foot view. We want to see what we can learn from the table. This is all just with clear glass, single, double, and triple silver coatings, which seem to be the main technology in the market today. I'm told by people I've shared this information with that something like a pyrolytic low E coating would be equivalent to the 1/8 to the single silver coating that I used for this particular simulation. So this was done using Berkeley Labs Windows software, and it contains simplifications to help us to see similarities and significant differences between the available glass options. So I rounded the metric U factors. I computed R values, inch-pound R values. I rounded the inch-pound R values to R5, and I began to see that whole clumps of data in my spreadsheet were all at the same R value. And so, and once you clump them together by R value, you're seeing that things like glass thickness and gap width aren't making as much difference as you might have thought they do. They do at the second decimal place, yes, but at the level of an R value, they're insignificant. And relative heat gain parameter. Okay. So we'll show you what the table revealed. I've ranked the products in order of R value, and we're comparing them against uncoated glass or uncoated double pane, single or double pane class. And so here's the R4 options illustrated. We've got dual pane with low E coatings either on one side or the other. Generally, when we want a really high solar heat gain, we're just using 1 silver coating on the number 3 surface. There's no point in putting low solar coatings on the number 3 surface. So these are the practical options that people are using. Then when we add a room side low E coating, so we've got coatings on 2 and 4, we're up at R5. At R6, we have our highest solar gain triple unit, which would have the low E coating on surface 5. And then we have we'll call it the passive house window, triple pane with 2 low E coatings on 2 and 4. And then we have, for those who want to brag about having an R9 window, just a little bit better than the competition, we can slap 1 more low E coating onto the room facing surface, and we're at R9, and we can brag about that. But do we really get much of value when we do that? So when we reveal all the numbers, we have this chart. And so what can we learn from this chart? One thing that we can learn is when we add a room side coating, we're dropping the indoor glass surface temperature. So with 1 low E coating, sorry, with a dual pane with 1 low E coating has indoor. Start at that point. There we go. Okay, that's better. So look at our double single glazing. The single pane window was at -9 degrees Celsius in winter, in a Chicago winter. The glass surface temperature of a double pane unit was 7 degrees. you bump it up to 12 degrees with a dual pane unit and one low E coating. Yes. Temperature outside is -18. Temperature inside is 21. So these are under NFRC simulation conditions for winter. So what we're seeing is that with one low E coating, we have a warmer glass surface temperature than double pane clear. When you add that low E coating to the indoor surface, you now have two low E coatings, slightly lower U factor, but you also have a colder glass surface temperature. It's as cold as double pane clear glass. Now, the good news is, unlike double pane near glass, is that when you get close to it, you don't feel the cold. And the reason you don't feel it is because of that radiant energy from your body that is going towards the window. It's not going through the window, it's being reflected off of that room-facing low E coating. So that heat mirror, invisible heat mirror on that glass, is reflecting your body heat back to you. So even though it's 7 degrees, you don't feel the 7 degrees, you're feeling your own warmth. But here's the rub. The air molecules and the humidity in the air don't know that. And there's a cold glass surface temperature, so it can get condensation. So that's why there's a condensation risk on that glass, is because the surface temperature is cold. And if the surface temperature is cold, you probably have a draft too. If that's a floor to ceiling window, you probably have a cold draft, because as far as the thermodynamics are concerned, it's like a double glazed clear window in terms of the draft potential based on glass temperature. Yes.
For the dual pane R4, the 3 silver, where are the coatings? Are on surface 2, 3, and 4, or where? Because it's equal in terms of temperatures. You're probably better off with a dual pane than a triple pane for temperature controls.
The 3 silver is referencing the low E 3 layers. It's not 3 separate coatings. It's like a 366. That would be a 3 silver.
Does that answer the question? Okay, good. Yeah. Yes, we're talking about the density of silver here. Single silver, double silver, triple silver is that silver density. It's kind of the 3 layers in which everybody in the low industry have products at those levels of performance. So we're talking about room side coatings. Now, to go from R8 to R9, we also have an improvement in the R value, an improvement in the U value, but the glass surface temperatures are still about 4 degrees cooler. Now, that is about the same as your double pane window with low E coating. So you've got a triple pane window, but you're not getting the full comfort benefit of a triple pane window when you've got that room side coating. So it's just something that people need to appreciate. There are cases where that will be meaningful, and there are cases where it may not be meaningful. But if you are looking at, let's say, floor to ceiling windows in a view property, then I would think it's probably not worth, just to get that extra R point, to have to live with colder glass surface temperatures, potentially drafts, potentially condensation. So there's a lot we can learn from this chart. And the whole beauty of this chart is, and why I want to share it with the public. And by the way, I have written a paper describing the technical side of the content of this presentation. Basically, what I'm telling you now, I presented a paper because I think looking at glass from this perspective can help everyone in the industry to just make better choices when it comes to windows. That besides just energy rating and U value, there are more things we could consider to make our lives and our homes more comfortable.
For R4, here it's for on surface 2. Do we get the same values if it's in surface 3? So this simulation for R4 is surface 2, correct?
Yes. So with surface 3, so you're looking at the R4, yes. With surface 3, you would be capturing more solar heat gain. But that's what I showed in this one here, right?
Yeah.
So this is a surface 3. Okay. So if you want the high solar gain, then you would be using the high solar gain coating on surface 3.
Al,
Yes.
I think he might have been saying, what if you use a 2 silver on surface 3 in a
Oh,
dual?
I see. A double silver on surface 3? I don't know. I haven't seen that done. I guess, it would be easy to find out with the window program, but offhand, I suspect you'd have less solar heat gain.
And you would get increased warming of that interior light because that coating is now warming the inside light.
And that
I've
might
done
be a
some
good
modeling
thing.
on
That
that.
might actually increase your glass surface temperature and make it more comfortable, potentially. I don't, but,
Have you ever run these numbers at like 0 degrees Celsius? And because looking at, if you did a psychometric chart evaluation at 7 or 8 degrees, that's about 50% RH can result in condensation, I believe. But if you run it at 0 degrees, you might get an inside temperature like Vancouver, it gets to minus 18 once in a decade for one day
Yes,
at midnight,
yeah.
and that's it.
Yeah.
So it's an irrational evaluation of performance. So if we're selling Surface 4 low E into a market that's mild, can we calculate the number of condensation hours potential in that region using realistic values?
So that's a good question. Does somebody who knows window better than I do, can you choose any environmental conditions you want? Or do you choose from a menu? You can? Okay, there you go. So that's a good point. This analysis could be repeated for different climate areas to get appropriate numbers, because you're right. This may not be a problem in a warmer climate.
Now, Anton, that was your Pacific point of view. So the Winnipeg point of view might be minus 18. That's nothing.
You take it down minus 30.
Yeah, take it down to minus 30 for us.
Touche. So because these room side coatings reflect, we've already talked about that. Let's go on to the next one. This is a weird thing. Okay, so room occupants don't send the discomfort because of their own heat being reflected back to them. Let's look at the high solar gain configurations. So single silver and other high solar gain coatings have high solar heat gain and high relative heat gain values and can lead to significant overheating discomfort when exposed to direct sunlight. And this all, the other thing that we need to think about in this discussion is the relative size of windows with respect to the rooms and buildings we inhabit. Because in a building built when everything was single glazed or double glazed clear, the windows were smaller because larger windows would have been too uncomfortable. Now, if you go and refit those older homes with high solar gain windows, or windows that might have a colder glass surface temperature, it might not be as much of a problem simply because the windows are smaller and the amount of heat coming through a smaller window is less than coming through a larger window. And so I think there's, historically, the older buildings can probably handle any kind of glass and it'll be a thermal improvement and a comfort improvement. But as you start to get to larger areas of glass, the comfort equation can turn the other way around. I did some calculations for the paper I wrote. I looked at products at the NFRC sizes, looking at industry average frame sizes, just for my experience in the industry. I figured out what the glass size would be, and I calculated solar heat gain coefficients and relative heat gains at NFRC sizes using the same glass types. That's in the paper. But basically a 2 meter by 2 meter NFRC size patio door has about 3 square meters of glass. If that was high solar glass, and we're talking about something like in the 490 range, this highest solar, you'd be pulling in what, 490 times 3 meters is almost 1500 watts potentially of heat. Now that wouldn't be every day of the week. It wouldn't be at noon, that might be on a west facing window, as the sun is setting and bangs right in there. But it just gives you an idea of the potential magnitude that solar heat gains can be when they're at their worst. And that we might need to consider when we're recommending glass for windows. Because if you're in a neighborhood where the sun never shines through your patio door, not a problem. the high solar glass is probably your best choice. There are entire neighborhoods where we've got small windows and things like that, and these aren't an issue. But we also have neighborhoods of new homes where, you know, the wrong glass causes huge problems. So high solar gain glass can be used for passive heating. Passive buildings are intentionally designed to capture solar energy and utilize it without causing occupant discomfort. Passive solar designs are supposed to use fixed or operable external shading to shade windows when solar heat gain is not required. From a comfort viewpoint, however, there is a significant risk of overheating if you use high solar gain glass in other buildings, especially with larger window to wall ratios and windows facing primarily one or two directions. I know that in Vancouver, the hoses are so big on the lots now that all the windows face front or back or both. Usually, most of the windows are facing one direction. And depending on what that direction is and what the glass is, you could have very different comfort outcomes. So we look at low solar configurations. The medium double silver and low solar triple silver coatings have 40 to 60% lower relative heat gain values. And these are the products that you would want to consider if you have a situation where there is potential for overheating discomfort, which would be large windows facing, you know, east, west, south. The glass surface temperatures of these products are a little bit warmer. And they're the warmest of them all, really, is these the options that I've highlighted here. With the exception of the ones having the room side coatings, where we do see a lower temperature there. So this is basically it. This is a chart of the main options that we deal with and the main metrics. And I hope that you can see how this can be useful in now having a discussion about comfort, where you can work with a homeowner, you can look at the kind of house it is, the size of their windows, and you don't have to explain everything to them, but you can use that to figure out if one of your products might actually be a discomfort to that owner. And maybe you can identify a comfort condition or be better off with a different glass option. This is really what I was hoping to do, is to come up with some practical, actionable guidance that you could use to think about potential comfort risks and what would be the glass product that would best mitigate that risk.
20 minutes up.
Okay, so choosing glass for occupant comfort. I'll just zip through this very quickly. The 3 ways low E coatings can improve occupant comfort. One is to reduce solar heat gain. The other is to reduce winter heat loss. And the third is to minimize convection and drafts. And so these are the 3 things that we are needing to think about when we think about occupant comfort. And all 3 of those are addressed by that chart. So I think I've said enough about that, because I'd like to give some time to our panelists to weigh in on this. Let's just maybe back up here. Basically, to minimize overheating discomfort, you focus on your low solar glass options. And to minimize cold discomfort, you're looking to warm surface temperatures. And primarily that. And if you don't want to think, if you just say, listen, this is too much work, Al, I don't want to think about this, my head hurts. I just want, what glass will prevent comfort problems, period. Overheating, cold, whatever, what is it? Then these are the ones. Choose your, if it's a double pane unit, single low E coating is fine. And in a triple pane unit, 2 low E coatings. And you will have the most comfortable windows. They will not have excessive solar heat gain. They will not have excessive cold discomfort. They're going to have the warmest temperatures. So basically, to my mind, this could be the basis of a how to sell glass seminar for window companies. One final point, our climate is changing. The passive house buildings and net zero buildings designed in the last few years in British Columbia are overheating. A number of them are overheating causing concern, but they've been designed using the climate data the building code requires you to use. And there's concern that the historic building code data is not reflecting the current climate. And so you can see where this is going. It's not 89 anymore. The concept of the energy rating was developed at a time when our climate was different than it is today. Since then, it's warmed considerably, and we know it's going to get much warmer. So we have to rethink our assumptions about the merits of passive solar heating strategies and begin to consider the risks on relying on it. Because we're building buildings that are still going to be occupied in 30, 50, or 80 years. You put in a good set of new windows from a good manufacturer today, they should be there for 50 years or longer. And, you know, the climate in 20 years, we know is going to be warmer than today. It's in 10 years, it's already warming. Montreal doesn't have the snow it used to have. I grew up here, and everybody here tells me winters aren't like what they were in the 60s and 70s. And that's this case all over Canada. So basically, climate change is dealing with our space heating problem for us. And our problem is going to be cooling more than it is going to be heating. I think that's another reason to consider passive heating strategies. And the last point here is that basically a study commissioned by UBC concluded that warming temperatures will likely lead to a decrease in heating demand by almost 1/3 and an increase in cooling demand by nearly 5 times over current demand levels by the 2050s. And that's in Vancouver. So, you know, there's a similar trend going on everywhere. So I think when you're thinking about the future, you have a product that's going to have a lifespan. It's better than any window product that's been built in the last, you know, half century. It's going to last a long time. Is it going to provide comfort, or is it going to create problems for homeowners? So I think we have a real good story to talk about. And we have good tools to recommend good choices to clients. And I'll just leave it at that. And let's have our panelists come. Yes, I'd like. Sure. Why don't you guys come and the mic?
Okay, great. You want to hold just for questions?
We're not panelists, we're a quartet, and we've just got a couple numbers we want to do for you this morning.
So we have a panel of 4. What are your thoughts, guys, on what this presentation about today? Just whatever you think of it, good, bad, or indifferent.
I agree, and I'll turn the mic off now.
No, Al, I thought that was a very good presentation for explaining it to lay people. You know, you're an expert at like dumbing it down and presenting it in a way that somebody has no experience in the fenestration industry is able to understand it. And I think that's a really good job. I personally tend to lose people in my presentations because I think that they think like me, they have my level of knowledge, and I forget that not everybody is from that book.
Let's get you a different mic.
Yeah, so I just want to say thanks, Sal.
Oh, thank you.
Yeah. That relative heat gain metric, there's something the matter with it. I'd like to look into that in more detail. Because I mean, watts already has a unit of time in it, right? 1 watt is a joule per second, right? So I don't see where you would multiply that, you know, by 60 by 60 to get the heat loss in an hour.
So it's oh, I see what you're saying, right? There's no time in it, right? Okay.
Yeah. So yeah, watts all the U value already contains a unit of time.
So
It's
doesn't
per
the watt,
second.
doesn't the watt have a unit of time?
Yes,
as
it
well?
does.
An hour,
1
right?
watt, no, 1 watt is 1 joule per second. And joule is a unit of heat energy or electrical energy or mechanical energy. And so you were saying that window has a relative heat gain parameter that does some kind of a multiplier? I'm curious about that because I took your, while I was sitting there, I took the U values. I multiplied them by 39 because that's the difference between 21 degrees Celsius and minus 18 degrees Celsius to give the heat transfer, right? In watts at that temperature difference. And I wasn't able to find a multiplier that got me to the relative heat gain number that was on the chart. So
I welcome you looking into it because I tried to do more research on it. It's very hard to find information on it.
Yeah.
In the paper, I have a calculation formula that was in the window 4 manual. And it was basically, I think 631 watts per square meter of solar energy times the shading coefficient.
oh, okay.
So
So it's
the-
looking at more than just the thermal transmittance.
it's not looking at the
solar.
thermal, it's looking at the solar.
Okay, I get.
Yeah.
So now I understand where
Yeah.
that is probably coming from.
But
You gotta-
anyway,
Now you got about 10 minutes.
okay,
So
so
want to get a
please.
couple questions.
Yeah. So here we go. Yeah. Well, I'd like to hear from the other panelists.
I thought it was actually a really good presentation. And just to go along with what you were saying as well, I'm not from the window industry. So I was able to follow along and actually understand what you were talking about. And what I thought was interesting was that there's really only 2 scenarios of those windows that you could choose that are actually going to be eligible for the rebates that are available in Canada right now. So the triple pane, as long as it has a U factor below 1.05 or less, qualifies for the tier 2 rebate of $250 per opening. Anything with a 1.22 or less will have a rebate of $125 per opening. So it's interesting that there's really only those 2 options, 2 scenarios, double pane or triple pane, with those various coatings that will actually meet those rebate minimums.
That's true, but there's also an ER path, which would open up a whole range of other products. But you're right. If you're only on the U value path, you're 100% correct, but they have an ER path as well.
Yeah, and you're right. It is either or. Yeah.
Yeah.
So
So
Well, I was going to say, I look at this from my own personal journey as a 10-year-old boy with a bedroom facing west and sleeping in the tent trailer all summer. So I know exactly what high heat gain bedrooms are like, and you don't want to live in it in July and August in Vancouver. That was in the 80s. So it's even worse now. And that was a 1980s house with a 5x3 window. So you can imagine in today's climate with a bigger window, what that means. When I jumped into the window industry, I didn't really know anything about windows. And so I just started reading and studying, and I started getting involved. It's probably around 2008. BC had a rebate program for replacing windows, and the ER path comes in, and policymakers are always looking for a simple box to check that makes it easy for what windows qualify for a rebate. And they picked Energy Star. Makes sense. And when I started studying Energy Star, I saw the ER path and I calculated and I went, what is this solar heat gain thing? Knowing that high heat gain is not good for a house, why is Energy Star rewarding a window for high heat gain? It didn't make any sense to me. And so as I started working with the utilities, BC Hydro and Fortis BC, about how they justified using that metric as a way of defining high performance, I kind of started shaking my head going, it's not high performance. Now that's at a time when air conditioning wasn't as popular as it is today. And I think now it's every new home being built in British Columbia has got air conditioning or a heat pump in it. All the rebate programs are putting heat pumps into houses, which means they all have a cooling load. Kelowna, for example, has more energy consumption in the summertime now than it does in the wintertime, and it's generally perceived as a cold climate zone. So scratch your head as to what's going on in these areas. And does Energy Star have anything to do with higher energy consumption using the ER path? And so when Al presented this concept of relative heat gain, like when I'm training a new sales rep who has no window experience and you're trying to educate them on this concept, they right away go to low solar heat gain is the better window. That's their interpretation instantly. But what does that mean when a customer sees the Energy Star brand and says, well, that window should be better, but you're telling me it's not? And so by translating solar heat gain into watts per meter squared and being able to demonstrate to people, like when we were talking, I got a space heater on my office floor because our heating system is so bad in our office, and I flip it over and it's 1500 watts. And so I'm like, are you telling me that a window could actually be the equivalent of a space heater plugged in on full time in July and August in our climate zone? And the answer is yes. So if you're sitting across the table from a homeowner who's looking at retrofitting their windows and you tell them that those 5 windows would be like having 5 space heaters plugged into your house all summer long, they're going to go, what are you, nuts? And so,
Of course, that's only if they're all facing west and it's between,
Yeah.
5 and 8 o'clock or something.
but even
right?
the concept of who would plug in a space heater in their house in the summertime, like by just putting it into those very practical terms, if you're ever training a sales rep on how to have a conversation with a homeowner to make their house more comfortable, that logic, as opposed to a solar heat gain of 0.18 versus 0.48 means this, like it doesn't mean anything to anybody in reality. So this is probably the first time I've seen a real logical explanation as to what solar heat gain actually means. And I think if you presented this at the Enercan level to BC, like the utilities that are using those platforms as an incentive to select product, they might start to realize that the ER path is not the correct approach to using product. So
Some people might disagree that having a space heater in Winnipeg from your window in the wintertime.
But summertime though, and that's the problem is we've always said, the West Coast it doesn't benefit from ER and everywhere else does. But now we're finding, Montreal has summer. Calgary has summer. Everywhere in Canada is getting summer and they're getting higher heat. So they've all got to be thinking more about the proper solar heat gain and U values instead of a high ER, because they're going to yes, they may benefit in the winter, but they're going to lose those benefits in the summertime.
I was just gonna rebuttal coming from Ontario with -40. The natural gas has gone up by 50%. It's going to continue in Europe. It's going up by 89%. They're talking about having more solar heat gain. The Americans are talking about it also. So I know it's we have to think for Fenestration Canada, it's all Canada, not just BC. Often on the panels and all that, it's very BC centric. But the other rest of the country, being Quebec, Ontario, Manitoba, etc., it is bloody cold.
Except
Now,
your Toronto-based manufacturers are complaining because we allowed them to put in Energy Star high solar heat gain windows, and now their homes are overheating in the summer.
and that's where we have to look at, percentage of surface of glass with the wall and where it's oriented. I'm open to that.
I agree. I think
But
it's critical. This isn't enough without an appreciation. To your point, it's not enough just to look at these numbers without an appreciation of glass sizes, window sizes, orientations, external shading, because I remember I was in Ottawa earlier a couple of months ago, and I actually walked by a house that had a Nordic sign, and they had replaced their windows. And I'm looking at the house, and I'm looking at the whole neighborhood, and I thought, this isn't like Vancouver homes. The windows are smaller, the window to wall ratios are smaller, and I'm thinking, you know what? There's probably no problem at all here with these issues. So I think the housing archetype, the generation of building, I think we need to take all those things into consideration before just having good glass and bad glass.
And it also depends on new builds or existing homes. So that's the big, like for us, it's home renovation, retrofits for homes. That's where Enercan is also spending all their money. They're not looking at new builds, but mostly at old builds. So that's where
I want to kind of elaborate a little bit more on I like to ask a question to architects. They know what a good U value is, but if you ask what's a good solar heat gain, well, it depends. But a lot of them will give you a number. And I'm kind of like, you scratch your head going, you need to know what the building is, you need to understand what you're actually doing. The problem with the solar heat gain coefficient metric is it's turned into a simple design metric of good versus bad. And when you talk about, West Coast versus like Vancouver versus Ontario, you're bang on. We don't get sun in the West Coast in the wintertime, but this policies are being blanket statements across. So you talk about we're all from BC, but the reality is policy is being written nationally now, which is starting to become alarming, where it needs to be focused in its own individual regionality perspectives.
Yeah, I'd like to just make a comment as well that it does sound sometimes like we're just talking about BC, but I think it's because the problem is bigger in BC. Rest assured, we can appreciate that solar gain to save energy in the appropriate place and window and orientation, et cetera, we're 100% behind that logic. So rest assured,
So
we're not missing your point.
What some of the designers don't realize is this: if you want to take advantage of passive solar heat gain, that's fine, but you better design your overhangs so that in the summer the window doesn't get that direct sunlight, but in the winter when the sun is low on the horizon, it does get that sunlight. So if you design your building properly, you can absolutely take advantage of passive solar heat gain. But people who specify based on ER and think that the equation and the hypothetical model house is going to take care of this for them are sadly deluded.
Well,
I just want
anyway,
to add
yes.
one thing
Yeah,
here
please go
too.
ahead.
A lot of what we're talking about today is very, very technical. And when it comes to actually selling windows to a homeowner in a retrofit situation, yes, you have to take all of these things into account and make the right choice of which window is going to do the right thing for them and be the best option for them. But you also have to understand that homeowners know that these rebate programs exist, whether it's Clean BC, whether it's the Edmonton HERA program, whether it's the Manitoba Efficiency Manitoba rebates, or here in Ontario, or not here in Ontario, we're in Quebec, but in Ontario where I operate, there are things that homeowners are going to ask. They want to know what is eligible. What are they going to be able to get that is going to satisfy the demands of their house, the solar heat gain, the U factor, the ER ratings, but what can they actually get that they're going to be able to save money on? Like, these are big projects that people are spending a lot of money on, and anywhere they can actually get a chance to save some money on per opening, they're going to want to know, what can I get? So when we're talking about selling windows and offering the right product, that is definitely a huge consideration that a lot of people are still slow to get on board with. So I just wanted to put that out there.
And they also have the credibility. They believe that anything that is rebatable must be the best thing for the home.
Yeah.
So if it has a rebate tied to it, that's going to be the answer.
Well, so thanks, everyone. Our time is up, but again, my goal has been, I want to present this information without bias and without prejudice to the energy rating or to high solar products, because honestly, the building I live in, when we replace our windows, I'm going to choose a high solar window because we get just a little bit of sunlight directly, and it's going to give us higher visible light transmission, and the U factor will be just as good for all intents and purposes. But when you understand the dynamics, the issues, right? We can tailor glass to meet individual needs. And I think I would like to see the comfort dialogue enhanced, where people can all talk around a set of agreed facts in a way that they can make good decisions in the future. So.
Okay, any last questions? Well, we're just about out of time, but if somebody has something.
Still planning to do a task group on this?
That's a good question. I think we need one. I think we need one.
Yeah.
I think we need one, and Terry can chair it.
Yeah. It is a really large issue and a complicated one. And, it has a tendency to kind of divide some of our membership, and, and I understand that. So yes, we're definitely going to work on it. It's just not going to be this year, but it's coming. Thomas won't
participate in. So
sure.
Yes.
Okay, we are out of time. I saw a lot of photos being taken. Just so you know, all of these sessions are recorded, and they'll be on our Fenestration Canada website in the technical section in about 2 weeks' time. So you'll be able to see them and hear them, and any photos you were taking, you'll be able to see the slides. Okay. Thank you very much.